Hello and welcome to this webinar hosted by SimScale on digital innovations in the design of sustainable buildings and structures. I'm delighted to be joined by our guest speakers today from Mott MacDonald. I'd like to introduce Benjamin Bleckly and Eugene Cullity. Ben, Eugene, hi and thank you and welcome for joining our SimScale webinar today.
Hi, Nagman. Thanks.
Thanks, Nagman.
Brilliant. Like I said, thank you so much for sharing your insights with us today. We're really excited. We've had a lot of interest in this webinar, so we're going to crack on with it very quickly. I guess before we jump in, I'm interested in hearing your opinions about what's been going on over the last year. So Ben and Eugene, how have things changed for you, I guess, since the first lockdown started? And generally, what do you see the outlook for our industry over the next 12 to 18 months?
Yeah, I'd say just firstly here in Australia, or particularly Adelaide, yeah, we definitely haven't been hit as hard by the pandemic as over in Europe or in North America. Or, yeah, probably most places in the world at the moment. So while I mean everyone's life's been affected by it in some way, our working lives have been as well. But things are actually not too bad over here. I don't know, what do you think, Ben?
Yeah, so things are definitely picking up. So when coronavirus first came about, we definitely did see a slump in the sector, especially in buildings. Nobody really wanted to get out onto construction sites. We're all in lockdown. There's no building work going, so a lot of projects went on hold. But in the past few months, and particularly going into the future with the vaccines coming out and now being rolled out, I think we're going to see all of that pick up again, just because people want to get out, especially governments. They want to, well, we're seeing here in Australia, a lot of money injected into building projects, getting things rolling, building infrastructure. So I think over the next, say, 12, 18 months, it's really going to pick up again.
Great. It's a positive outlook. That's great to hear. Let's jump in and see some of the fantastic work that you've been doing. Before we do that, let's take a few quick introductions. So let me tell you a bit about SimScale. We're a German software company founded in 2012, headquartered in Munich, and we've created the world's first cloud-based engineering simulation platform. What that means is you can do simulation, things like CFD, solid mechanics, thermodynamics, and that's all accessed via your web browser. So it's an online simulation tool used for analysis and collaboration. Now, why are we here today? Today, we're talking about sustainable buildings and structures, specifically how Mott MacDonald, one of the biggest global engineering consulting firms, uses tools like SimScale and other simulation tools. So I'm going to hand over very quickly to our guest presenters, Ben and Eugene, to introduce themselves. And then let's take a look at some of their projects and how they're using simulation. And we'll take some questions and answers from the audience. And then right at the end, I'm going to let my colleague very quickly do a short briefing for the thermal comfort hands-on workshop, which is happening next week on the 23rd of March. Great. So I'd like to hand over now to Ben and Eugene from Mott MacDonald. Thank you.
Great, thanks, Nagman. Great, so great, thanks. Okay, so hello to everyone that's tuning in, or you might be tuning in to the recording later on. Good morning if it's morning, good evening if it's evening, wherever you might be. So Ben and I are working in the engineering sciences team here in Adelaide, Australia, and I guess while I guess my title would say sciences engineer, I'd say I'm pretty much a CFD engineer or a CFD specialist, so doing a bit of other work on in the wind engineering space. Ben, I guess you can introduce yourself if you'd like.
Yeah, so I started out as a CFD engineer at Mott MacDonald. Now moved into more sort of digital innovations, looking at smart infrastructure, that sort of thing, especially in the wind engineering and wind tunnel area and fields. So Mott MacDonald themselves, we're an engineering consultancy, we're global, so we've got offices in 135 different countries. Head office is based in the UK, but we've got right across North America, Canada, and then Europe, Asia, and Australasia as well. So we're trying to improve society for considering social outcomes, focusing on excellence, and in particular, so digital innovation, which is where all the CFD simulations, smart infrastructure comes into it. And we're going to focus on sustainability in that terms of things.
Cool. So I will give a brief overview on some of the work that we do in the sciences team here in Australia. So I guess starting with CFD work we do, here you can see in the top left, we're looking at ventilation in tunnels, plume dispersion studies, pedestrian wind comfort, ventilation of stadiums at the top. So that's something Ben will be talking about a bit later, as well as looking at thermal comfort in large stadiums. And down the bottom, we've got a clip from a car park ventilation study, I believe, which is similar to plume dispersion in a way. I guess some of the other work we do physical wind tunnel testing. Sometimes that's coupled with our computational pedestrian wind comfort studies. So that can be for, looking at the structural dynamics of tall buildings or facade loads on large structures. And we can also, we've also looked at loading on long span trusses and stadium structures and other large structures there. On the bottom right, bottom right, it's that is a sound level meter. So that's we do asset monitoring work or really getting into the smart infrastructure space. I'd say looking at very large data sets on assets there, looking at rail projects and such. But yeah, today focus will be on natural ventilation in stadiums, and I'll be talking a bit about thermal comfort and looking at underground stations as a case study for those.
So Eugene mentioned some of the projects that worked on some of the areas that we work in, and this sort of mind map sort of shows all of that in sort of broad terms. So you got the expertise and sectors and how we link it all into the opportunity, solution, outcomes that we provide to clients. But what I really want to draw your attention is to that outside ring, which is the big issues that Mott MacDonald see facing, well, the company as a global thing, as well as like the entire global population as well. And we really only have one focus on there, that's sustainability. With all the development goals within the UN, also linking climate change and everything, we're trying to look at a more sustainable future, and also particularly in the built environment, building sustainable buildings, so harnessing natural resources, so air movement, temperature, all of that, so we don't need to mechanically ventilate buildings as much. We're not oversizing mechanical plants, and we're really driving down the energy of building uses. So I'm going to jump into some stadium work, so looking predominantly at pitch health and internal patron thermal comfort, so we can adapt buildings to achieve more sustainable and beneficial outcome for clients.
Ben, that was a fantastic slide you showed earlier about the big thinking at Mott MacDonald. I think it's really interesting, everything that you're doing. It represents the depth and breadth of capabilities. Where does simulation fit in to all of that? Not just CFD, but I guess the importance of analysis and simulation tools to help meet all those goals and different types of analysis you'd have to do at a multidisciplinary team like Mott MacDonald. Perhaps you could comment on that. How important is simulation in general, not just CFD, to everything you're trying to achieve?
Yeah, so if we go back to that slide, just looking at here, you can see, so CFD and simulations in general, you can sort of link in across all of the sectors that we've got there, so environment, climate, resilience, as well as it comes in under all of the expertise as well. So you can look at transportation simulations, so car movements around sort of car parks, road transport simulations, see how it's going to be used by trucks, buses, cars. And then in terms of buildings, you can look at sort of using parametric models as well as CFD models. So you test a large data set of design parameters, assess them against key performance indicators, and that helps you to select a preferred design. So which case is typically better outcome for the client than just running a single CFD model, not iterating through the design, not assessing using simulations, because simulations typically give a more robust, more accurate, and they're also more time efficient than doing hand calculations and working through projects that way.
Yeah, fantastic. Thank you, Ben.
So moving back onto stadiums and looking at pitch health in particular, any sort of sustainability, one where you want to harness natural elements of the environment. So you got to look at climate analysis. So predominantly this is wind, and we've probably all seen wind rows like this. I know SimScale uses it in the pedestrian wind comfort. So if you use that platform, you'll have seen it. But analysis of this, looking at both magnitude and directional probability of the wind, enables you to analyze it, see where the predominant wind direction is, if there's any secondary wind directions, and then you can look to design your building to capture wind predominantly coming from that region, and then funnel it into the different areas that you want ventilated, so into stadiums, across the pitch, or into the stands to cool down your patrons while they're packed in once COVID has run its course, packed back into stadiums and enjoying the atmosphere. So a similar thing is done for temperature. Make sure you're not overheating anyone, or as well as getting the solar luminance on the pitch that you need. The third point there that I put is future climates, and that's particularly important now as we're looking at climate change. And these are some of the predictions for the future temperature. So global surface temperatures are rising. We've got stronger storm events, higher wind speeds as well coming across. So in terms of building design now, we've really got to think about when is the building going to be used, what is it going to be used for. So if you're looking for designs, buildings that are going to be in operation in 2050 up to 2100, you're looking at like 3-4 degrees of extra heating that we need to account for when we're simulating the building now. Instead of using historical data sets, which are typically cooler, we got to look at future data sets to make sure we're still maintaining nice, comfortable temperature for patrons. So where does this all link into? So it comes down to performance metrics, particularly with pitch health. Sort of not really set what sort of probability exceedance you should be using, but turf suppliers would typically provide you with a wind speed range that's ideal for growing conditions. So we need to pick what probability we're going to use. So with 90%, you got lower wind speeds, going up to higher wind speeds at 10%, but what does this actually mean? So 90% exceedance, so 90% of your wind speeds are going to be greater than what is shown. 10% probability exceedance, only 10% of your wind speeds are greater than what is shown. So in terms of looking at an average speed across the turf for an annual year, you're probably looking at around the 50% probability exceedance and trying to run from that. It's also useful to note if you've got, say, this is soccer pitch and you're looking at a football pitch for you guys over in the UK. This is looking at 10%, you've got a windier sections around the goals and less wind movement along sort of the flanks or the wings there. So if you've got a particularly windy day and you're trying to kick for goal, you're going to have a lot more difficulty, particularly with this stadium design, because you've got a stronger winds. But that comes down to what I'm terming smart design here. So this is an iterative process that you can use. It works well specifically for simulations because you can run multiple simulations at the same time on a cloud server, look at multiple different designs quickly, and you can go from this design one, so this initial design, got high wind speeds down in bottom left corner, low wind speeds up in top right corner. This sort of design needs mechanical ventilation to grow your turf correctly. So that's large energy costs, large upfront costs for big fans to ventilate it. You do lots of iterations, you can move on to better design. So this is just an arbitrary design that comes out of that large data set. You can see we got changed louver design. So you're funneling, using that windrows, analyzing where the wind's coming from, funneling it onto the pitch. You got a more even spread across the pitch, and therefore you don't need mechanical ventilation, which is a huge cost saver. Ongoing costs are much reduced. I'm going to pass over to Eugene to talk a bit more about underground stations.
Great, thanks, Ben. So I'll be talking a bit about underground stations as a case study for thermal comfort assessments. Like I say, interesting in how complex the thermal conditions are within them. They kind of exist at this intersection between transport network design, building design, and urban planning in a way. I guess because of the complexity of these projects, there's the opportunity to have a great influence on the project outcomes and sustainability outcomes, of course, through computational engineering, in that, you know, the more accurately or the better picture you have of the environment you're looking at, you know, the better your design outcomes and the more optimal your design outcomes are going to be. And I guess that's, you know, that's what we all love to do, working in computational engineering. So in terms of the problem we're looking at, it's interesting in that you have a lot of different thermal spaces within a station. So stepping off a train, which is a conditioned space, into a platform area, you may be walking through platform screen doors, as shown in that image there, traveling through an escalator at it into a kind of large open concourse area, which may be kind of open to external conditions, or have this kind of interface with external conditions. And I mean, each zone is thermally different. A person traveling through these zones will go through on a journey essentially, and you know, we don't want that person to experience any thermal shocks. We're at the position now where we can kind of control that person's experience kind of at each point or throughout their stay in the station. What's interesting as well is you have these very dynamic or transient thermal conditions existing, particularly on the platform space, due to the movement of the trains and the interaction between the tunnel air coming in and out of the platform screen doors, and also your supply air as well. And the client will want to make sure you can meet very specific criteria that are able to kind of measure comfort in a very kind of dynamic space, and that might be, you know, at a specific point in time in a specific location, and it could be looking at, you know, the concentration of supply air and the airspeed as well. And I guess the role of the simulation is to get as accurate a picture as you can actually answer all of these things with confidence. So I'll talk a bit about the setup or the modeling approach. In terms of boundary conditions, you've got the boundaries to external or ambient conditions, which are really interesting, and I guess the way that pressure or temperature could vary based on, you know, the wind conditions or the external conditions throughout the year. You know, how do you model that in a way that accurately represents the influence that's going to have on air entering or exiting the station? And at the other end, there's the platform screen doors as well, and the definition of how the air's coming in and out of that part of the simulation domain, and at what temperature at what velocity. You've also got to define boundary conditions. I guess each surface has a thermal boundary condition, and that's I guess the thermal conditions are influenced by the soil temperature, by the lighting and equipment, and by the people inside the station itself. So there's a lot going on, and there's quite a large computational requirement. You know, you have to run a transient simulation to be able to see the effect of you know, the platform space recovering after the doors, after a train departs. We also need quite a fine mesh resolution around the supply air terminals, and that creates this problem with, you know, you have to have very small time steps, and which means a very large, you know, computational requirement. So cloud computing is really essential to be able to get, you know, model this stuff accurately. So at the end of the day, we're able to provide graphics like this, which when you're measuring supply air concentration, say using a passive scalar element, you can then contour by supply air concentration and look at plotting other variables on that. So the graphics are able to show, I guess, quite impressive or convincing way of demonstrating that you're actually you know, able to get an accurate picture of what's happening in the space. You know, using these methods, we are actually able to kind of tick off at every criteria and say, not only are we sure we're getting enough supply air coverage in the area, we can say exactly how much there is at every single point, or, you know, what temperature there is at every single time step, you know, after the train departs as well. And then with this information, you can start reducing your equipment sizing, or your, you know, increasing your cooling temperatures, and, you know, getting your design to a point where you're really on, I guess, on the cusp of an optimal design, which is, I guess, where you want to be operating in terms of sustainable building design. So I guess this is a very specific application in terms of the boundary conditions, or the influence of different areas in this space. But I also think this kind of modeling approach can be applied to a lot of other areas where you do have transient conditions. You know, it could be kind of internal and external spaces where you could have kind of gusts of wind, which carry external air into a, you know, space that you're wanting to condition, or any kind of problem where you have, you know, essentially a pool emptying and filling in terms of your conditioned air.
So yeah, that's Eugene's talked about those transient spaces. We're looking at sort of the stadium application using natural ventilation. You can also look at car parks. So we've done a couple of different car park simulations looking at pollution dispersion and harnessing natural wind movements throughout the building to disperse the harmful gases. That's particularly useful because it saves the cost of expensive jet fans or shaft ventilations, which is the image that Nagman was showing on the introductory slides. A few different variations of how you can get the mixing and dispersion throughout a car park without actually installing the mechanical materials. Another interesting aspect are greenhouses. So you can definitely use CFD and simulations to measure and simulate the humidity, temperature, wind environment inside greenhouses, and how the external environment will impact that. So you get the perfect growing sort of situation for the plants that you're building, especially if they're not native to your region. So that wraps it up from us. We've just got our contact details up there. So if you do have any other questions, feel free to reach out to us. Pass back to
Eugene,
Thanks,
Yeah,
Ariane.
thank you so much. Thank you, Eugene. Thank you, Ben.
All right,
Some
thank
fantastic,
you.
thank you. So some fantastic applications of CFD there, and it's really great to see bigger and more complex applications rather than just the building level. I guess a couple of questions. If we maybe go back to the slide on other applications that you had, I think it was the one before this. Yeah. This is a good place to discuss. We have some questions coming in from the audience about steady state simulation versus transient simulation. One of the questions is how easy is it to set up and run a transient simulation, and under what circumstances would you do that as opposed to a steady state simulation?
I think in terms of transient simulations, I think, yeah, perhaps the second part of that question is more pertinent. So in terms of, is the space you're looking at a transient space? What's actually happening in that space? Is there, conditions that, is the space recovering from a certain event, kind of air rushing in or air rushing out in the case of thermal comfort? Or perhaps for pedestrian wind comfort, is there, conditions changing from, gust wind effects that are particularly important rather than just considering mean wind speeds? So I think, yeah, that perhaps the approach should be just ensuring that you're modeling what's physically important in the system you're looking at, rather than oversimplifying or trying to force a square peg into a round hole, maybe.
Yeah, absolutely. And I guess a broader question from that is, which projects, how many projects that you work on do you use CFD
on? In terms of, the projects we personally work on, or looking more broadly at what we do in Australia.
Yeah, a bit of both really. So I mean, some of the big projects like you have on the screen now would lend themselves really well to doing CFD analysis, right? You have big open spaces, full height spaces, transient spaces. So doing a CFD analysis on that would be great. You must have other projects as well where it'd be nice to do CFD, but you don't necessarily do a CFD analysis. So I guess it's always that question about how much time and resources to put into a particular project. Obviously, we'd love it if we could use more and more simulation tools. In general, really, how do you decide which project needs a CFD analysis?
Yeah, I guess that's an interesting one. For us, I guess I'd say the bulk of the work we do in CFD would be in pedestrian wind comfort, because that's kind of established. There's always a requirement there in terms of legislation. What it would be, what we'd be like to be doing more of is, getting involved in projects at an earlier stage and kind of working more collaboratively, or using these tools to kind of run a lot of iterations, and being able to work with architects or clients to reach an optimal design. I think often we could be using CFD on a project, and we'll kind of set up the model and provide results, and people may then realize how the importance or the capabilities of what we're doing here. I guess that's kind of part of the vision in terms of looking at digital twins and going digital in general, is that these kind of tools or analyses become more integrated in the whole process.
Great point. Actually leads us on to another good question. So like you said, digital tools, you're using a range of tools and analysis techniques to to work on your projects, and I guess at some point those tools need to talk to each other or communicate and even exchange data, I guess. So two questions that come off that from the audience is, do you use CFD with other tools? Like, are you using the results from CFD into import other tools, for example, building simulation thermal modeling tools? And secondly, how important is it to have a tool on the cloud that's accessible to multiple team members and accessible, especially what you said earlier about working remotely? So I guess we're talking now about the infrastructure these tools are built in and how useful that is on the cloud in collaboration for the projects you're working on.
Yeah, so I'll just jump in with that one. Also a bit on the last one as well. In terms of projects that we can use CFD for, is also a lot of bespoke work where other sort of technical workflows don't really work. So we've done a couple of sort of like helicopter downwash simulations, more sort of arrays, looking at flow around arrays of either like satellites or antennas on buildings or sort of wind turbines, that sort of thing, which you can't really do hand calculations for. Those bespoke sort of simulations are right up CFD alley as well, and also very interesting to do. But answering the questions you've just asked, so these are, sorry, I've sort of forgotten what it was. You have to just repeat it. I got carried away with the interesting CFD projects.
Absolutely. Yeah, we're talking about the CFD on the cloud, I guess, right? So being able to access the tool from anywhere remotely, collaboration, and also how that works with some of the other tools you might be using, right? So using CFD generated results, data to feed into another analysis that you or maybe a colleague in a different team might be doing.
Yep. So in terms of cloud, CFD, incredibly useful. Being able to link into cloud servers, you can run large simulations very quickly on, say, 9628 core machines. A lot cheaper price than sort of the upfront costs that you might have to set up a HPC inside your work environment. Also, it's a lot more scalable. So we can run, especially with SimScale, we can run multiple simulations at the same time. Whereas if you're working on, say, a local desktop computer, you have to wait for the first one to finish before you can set up the next one and run it.
Mm-hmm.
So definitely much shorter turnaround time for simulations using cloud-based program or cloud servers, essentially. In terms of using results in other ones, so other software, there's Rhino and Grasshopper, which is parametric modeling software. You can pull down cloud CFD results and plug it into Grasshopper models that you've made. So you've got actual accurate results instead of using sort of standards, so Australian standards or ASHRAE, ANSI, or the UK ones. They've got default values that you can use in sort of wind analysis studies or thermal comfort studies, which says, oh, this is the wind speed here at this location. These are the sort of temperatures you should be using. Use simulation on this, whereas they're typically very conservative. So if you're using those, you're typically like over designing your building. So if you pull in CFD results, you can not only get accurate wind data in every single point on your simulation plane, you can also get accurate temperatures to use in UTCI calculations, or if you're using structural loads simulations, you can use that to design sort of your beams and your trusses inside the building or in long span buildings, particularly stadiums. So you're not over engineering and sinking a lot of, well, in terms of sustainability things, sinking a lot of carbon and using a lot more energy than what you may potentially need to use.
Yeah, and I think that's a great explanation of, it ties into your earlier big issues that you mentioned about Mott MacDonald. You're working on so many different types of projects and different types of analysis. Having these cloud tools that can talk to each other and communicate, or even import and export results is critical, because like you just said, you know, a building or a project might require, you know, thermal comfort modeling, ventilation, transport, wind loading, PwC, structural, so many different types of analysis. So having the tools there is so important to be able to do, you know, the work that you do and push the boundaries of, you know, sustainable design, which is what one of the things we're talking about here. Fantastic. Should we take one more question from the audience? It's very specific, actually, on natural ventilation, something you've touched on a couple of times. So something like the image you have on the top left here, you know, these big full height spaces where, you know, a lot of people might be using thermal modeling tools, you know, the energy simulation tools, which have quite a simple treatment of natural ventilation. But obviously, we know that you would need something like CFD on a space like this. But still, in the industry, you still get most people, most designers using the very simple and basic tools. I guess the question is, what is some of the dangers of doing that? Would you end up undersizing ventilation if you weren't using the right tools for the right job at the right time?
Potentially. I mean, that's the simple answer to your question is if your simulations aren't accurate, then really don't know what you're getting out. I think there's also the question of, you know, how are your CFDs being done? So you talk about, you know, more basic, they could be kind of bulk air type thermal models, but there are also kind of more primitive CFD solvers available in some packages. And you know, as you know, CFD users know, there are so many things that can go wrong with what software you're choosing and how you're actually setting up your simulation. So yeah, I think, and sometimes that kind of gets lost by the time that the results end up make their way to the client. So I guess it's important to do your CFD right, make sure all your inputs and your methodology is correct, and make sure you're actually able to communicate that, you know, why, how important everything you're doing is in getting accurate results.
Absolutely. Fantastic. This has been really useful, Eugene and Ben. Thank you so much for sharing your projects that you've been working on and your experiences with simulation, SimScale, but in general as well, sharing your knowledge and insights around the industry and some great tips there for other CFD users. I think we'll finish the guest presentation there. Again, thank you, Ben and Eugene, for joining us today.
Thanks, Dan Brown. Been a pleasure. Cheers.
Thanks very much.
Thank you, and all the best in some of the fantastic work you're doing at Mott MacDonald. Thank you to Ben and Eugene. What we're going to do now is talk about this part of this webinar series. There's a part 1 and part 2 workshop on thermal comfort, and my colleague Ajit will run through very quickly a short briefing on what that will cover and how you can join this workshop, which is a hands-on workshop. So you can sign up to SimScale step by step. We're going to take you through setting up a simulation, running a thermal comfort analysis, and I'll hand over to my colleague Ajit to take us through that.